My name is Yueshi. Very much thank you, steering committee for inviting me to give a talk for this conference. I must say before I start, so I have a very limited expertise in robotics itself. So my research is mainly about distributed computing, cloud computing, big data analysis. But I do enjoy this opportunity so that I can tell you other side of the story. So this conference is about cloud computing and robotics. So I'll try to give you some ideas about cloud as a very large-scale distributed computing system and what are major issues associated with such systems. So we have to make some improvement so that make clouds become more suitable for robotics. So I'm Professor Computing at the University of Leeds, so in the UK. Well, weather here has become much better now, so the UK is quite cold, quite chilly. Leeds is around the Midland of England, so it's not too far away from London. So if you take a train, not a really high-speed train, take the train, so around the 2 hours journey between Leeds and London. Leeds University is one of the largest universities in the UK. We used to be the largest until University of Manchester merged with some other local universities, so we become second largest. So within universities, I have my own research group with the name Distributed Systems and Services. So that's a small picture, says current members of the group. Yeah. So amongst our various activities, we have an international research center, particularly in the area of cloud computing. So, so far we have been there for more than 10 years now. So it is collaborations between universities and a very important company as Alibaba. So that we do have this luxury to carry out our own research through industrial partners. I personally, actually, around 2 years ago, I spent 1 year sabbatical within Alibaba. So get my hands dirty, play with their very big data center inside the company. So I'll give you a bit more details about what we are doing. So talking about cloud data centers, yeah. So nowadays, we could, within my research group, we could have a mini cloud system. So it's a lot bigger with 100 servers inserted inside such a system. But that is not the system I'm talking about here. So we talk about very, very large scale, massive scale of data center systems. That is a computer system with hundreds of thousands of servers connected. Yeah. So that's just show you a picture. That's a Google data center. So we do have very tight connections with Google with adapter, which is a data center located in UK, and also Alibaba data centers. So I hope those sets of data give you some ideas, the massive scale of operational data. Yeah. So we have the data, for example, from Google's for about a month. So you talk about more than 12,000 servers involved, then many much bigger number of tasks. Yeah. Data center within UK is smaller, but we get data like a year data also. You think about TB, PB level of data we have to deal with. So we have another 2 months of data from Alibaba as well. So that gives the idea of the data. So before we start moving into data, we have such a data about 4 or 5 years ago. Yeah. So we start our research into cloud computing and massive size of data centers. Through our researches, we kind of identified there are 2 key issues attached with such a system. So the first one, we realized existing research and also practical work do not really fully understand the customer behaviors. So when you talk about customers, you talk about the external applications, include those applications for robotics. Okay. So all the management and the designs at that time, they primarily focus on physical assets. They do not really adapt and learn to the changing behaviors, for example. Yeah, so our research is trying very hard to address those gaps between enhanced data analysis and also nowadays very popular words like AI. Yeah. So in the hope we can produce much better systems which could automatically learn software, hardware, users, and so on, particularly understand their runtime behaviors. So I try to give you some examples. When systems become a large scale, their behaviors, particular runtime behaviors, become very complicated. So with such large scale data in hands, you would be able to, I use the words you would be able to, yeah, not necessarily you can achieve that. When we first to have the data in hand, we actually took a big risk. Yeah? So you have a large set of the data. You don't know, how much useful information you can get really out of such data. Yeah, make it, useful sense of the data. So there was a use case. So lucky enough, so my team spent about almost a year. You have to be precise, around 10 months before we started to generate some meaningful results. So if you look at those diagrams, so we were able to generate very good understandings about software itself, for example, understand some important attributes of workloads run over a data center. Now we also understand better user behaviors, so you can see those dynamic changes from various and different categories of users. Yeah. Inside the systems, you can also find the important information about energy consumptions, about very high failure rates attached to such large-scale systems. Also, you can spend more time, go through entire system life cycle, to understand, again, different attributes of the system. So we did some scientific researches. Through data analysis, we started to create some models, try to build up, not only understand each behavior associated with the data center. We really try to find the correlation between different behaviors. Such model like we try to understand whether there is a correlation between users and the tasks. Okay, and also we were able to classify different types of workloads, which are quite important. For example, to understand the workloads better, we're trying to find out which type of workloads are actually CPU intensive or some others become memory intensive. It's very much like data oriented. Yeah, some others probably is networking incentive. So you can really classify different categories of workloads. So looking into those sets of data, so basically you really want to find the depths of those sets of data. You could really start to understand, for example, about the pattern of task submissions. Okay? And also try to find out the realities, how users, customers make use of large-scale data center, such as we noticed the one very important phenomenon like overestimation. So particularly for a typical application user, they normally tend to ask much more resources. Just in the case they think there will be some the peak requirements. But in reality, they make use much less of the actual resources from the systems. So through it was fun. You can find something you didn't really know before until you have to get your hands dirty, moving into the data inside itself. And also, of course, we can get more precise figures about resources utilization, like CPU utilization, memory utilization, etc. So I carefully list some papers we published because the limited time of today. So if you would like to find out more details, yeah, you're more than welcome to read those papers. So within my group at Leeds, we do perform research with the robotics side. We are part of UK National Robotics Facility. It's like a research centers, so the government put huge money into it. We also have our own driving simulators. So you say that's a big dome within the rooms. Actually, we have the cutting half of the real BMW cars inside that big bowl, right? So it's very much like life, the game players. So inside that bowl, you can drive the cars within different simulated environments. So you can drive your car in winter conditions, for example. Yeah. Secondly, we have our own, experimental driverless vehicles inside the campus of the university. So that is the university campus. That particular building is our newly built car parking buildings. So we are run two experimental parts, if you like. So it's electricity driverless vehicle. We have, we can host up to 4 passengers inside the parts. Yeah. So my team's responsibility is to design onboard software, plus wireless connections, plus particularly software in the backend cloud data centers. Yeah. So the big challenge for us is to guarantee the time requirements. Yeah. So fulfill the real-time constraints, and also make sure the quality of data processing and the transmission between the driverless car and the backend data centers. So I didn't get too much involved with these areas, but this is a key topic of this conference. So I pick up cloud robotics definitions. I could meet my colleagues today, probably this evening. I bump into Professor Bo Lin at NUDT in China. So we start to have some collaboration, particularly in the domain of cloud robotics. A lot of buzzwords, if you like, is so-called edge computing. So if you look at this diagrams, so from very much the edge, we have the particular applications such as robots, right? So if you consider that is a timeline, yeah. So from robots back to data center of computer, you would notice some different requirements in terms of latency, yeah. So for some particularly robotics applications, we might have a very strict requirements on latency, like very, very low latency must be ensured, must be guaranteed. Then gradually you probably move to back end of data centers. Latency might not be an issue. So if you think about some offline planning, yeah, like road planning, and also to perform some algorithms about weather forecasting, etc. So those applications wouldn't be that the time critical, yeah, unless you really drive a car. Having said that, yeah, so from the angle of cloud computing, we do not want to find any excuse to say, right, yeah, we do not deal with any real-time applications, so forget about that. Actually, we do care about many things which are major concerns within any robotics applications. Yeah. But today I try to cover two very important related areas within cloud data centers. Yeah. So first issue is how do we deal with potential high latency within a large-scale data center? Then secondly, I will also try to find a way to deal with this very normal high failure rate within a massive scale data center systems. So let's go through it one at a time. So first one is about this high latency. So from very front, the application devices, then back to data centers. So there is a high latency challenge there. So in our communities, the latency issue, we have the name is so-called a non-tail problem. Okay. So still think about very big data center systems. So within such systems, very simple concept here is to consider a job consists of many tasks. So think about hundreds and thousands of tasks. So the beauty of a data center is, so if we are able to partition a large job into many smaller tasks, then there is an opportunity we can perform those tasks in parallel. So over hundreds of thousands of servers. In the hope you can finish off such a job very quickly. Yeah, because you carry out those tasks, say at the same time, but on different servers. But that's only true in theory. When you are really to have a large-scale data center, okay, When you really carry out hundreds of thousands concurrent tasks inside such a large scale system, you immediately observe a phenomenon which you don't easily quite understand. Is no matter how good your algorithm, your scheduling algorithm is, you found that actually the final result is quite slow. Yeah, doesn't matter how you move your task along. You would observe always have this long tail. Okay, so imagine to be able to finish that particular job, you have to wait the last task to finish. But if there is a very long tail, then the whole point about quickly finish off this job, yeah, become no sense. Yeah, that is true in reality. It doesn't matter. You noticed there is always some slow coach. Okay, so
sorry, but is this meaning that you have found something like a critical path in your application that you cannot squeeze more, or is it because of the management of the?
I will try to give you a reason. Okay. There are so many reasons behind that. Mm-hmm. Yeah, okay. I can, if we think about, in a simple way. Right, so within although we have thousands of servers, probably some of the servers are just simply too slow, too old-fashioned. Then if we find a way of identifying such servers, we can replace it with much more powerful servers. Unfortunately, yeah, that is not a solution. Yeah, so in the case of replacing slower servers, let's assume you identify those servers. Suddenly you'll find out the next day you get a long tail again. Okay, I'll give you a reason. Okay, I'll give you a reason. So long tail is very bad, of course. Okay, it delays job computation. It will violate quality of service requirements. Yeah. You will face some timing faults, particularly in the case of robotics applications. And also because it's too slow, if you cannot fulfill the tasks, then you just simply waste the resources. So it's some kind of one-off phenomenon, or it's quite typical? Unfortunately, the long tail is very, very typical in a large-scale data center systems. So we're looking into bigger sets of data from Google, from Alibaba, from other open source cloud clusters. So it's a platform at CMU. Yeah. So we have we try to get evidence from different types of data centers. So we actually realized the long tail problems, okay, happen all the time. Doesn't matter what type of data centers you use, okay. And also the problem is quite serious, yeah. So if you look at those numbers, so at the level of tasks, we might have around between 3 or 5% of delayed tasks. But they do affect a much bigger proportion of jobs. Okay, as you can see, delayed jobs is normally around between 35 even 50%. So basically, simply to put, if you have the number of different jobs, the chance is 50-50 you will get a long tail for your job. That is that series. So we're talking about the use cloud for robotics. If we do not find solution for such kind of very typical problems, how on earth we can guarantee the time requirements, time-related requirements? Google published a report. Actually, they produce very good papers in the journal. It's called Communications of ASCM. Right? So they are engineering. Okay, they are engineers. They are not a scientist. Okay, so their job is the report under title "The Long Tail Problem." Yeah, computing at a scale. In that very good papers, they basically list so many possible reasons, okay, of long tail, but without giving any in-depth analysis. Okay, they say possibly there are such and such reasons. So we are scientists, so we have to do a much better job. That's what we did. We analyze those data, identify the reasons, then also identify the potential percentages of different reasons. And also we did one more thing better, is also identify the consequences of different reasons. So some reason, for example, might happen rarely, but if it does happen, the consequences could be, severe. Like the tail could be very, very long. Yeah. So we list different reasons. For example, think about different workloads. If workloads are CPU intensive, then if you put those workloads all together in a certain group of servers, they will compete with each other. So when you observe such large-scale data centers, you actually look through some servers are very busy, so running out with high capacity all the time, but unfortunately they do not deliver results. So it's very much you drive your car very hard, but your car moves very slowly. Yeah. So that's one particular reason, for resource contention. Another reason is so-called data skew. Yeah. So you can start your applications by carefully balance the data sets so that you make sure each server has more or less a similar amount of data to process. But you do not have control over intermediate data, because each different task might generate different volume of the data. So from time to time, some of servers might have to handle much larger volume of data, hence slow down its process. Yeah. So that's happen not necessarily very often. We realized it's around a small percentage, but if it does happen, the tail becomes very, very long. Another in-depth research we also noticed, actually it doesn't matter if the computers or servers within the data center have different architectures, different types. So those diagrams we show 3 different types of server loads, but you notice that you always have the different long tails there. Okay, so that gives you another ideas. So the long tail doesn't necessarily be associated with a specific type of servers. So it's quite general phenomenon of servers. The challenge becomes even much more difficult when we analyze those data and play with the real system with Alibaba, for example. Then we noticed the long tail happen all the time, but unfortunately, who generates the long tail, the servers, the number of servers who generated the long tail change all the time. So it's very much like a human being. When such a system becomes very large, so today as a saver, if I'm in very good health, I probably perform well. I don't generate any long tail. But tomorrow I feel down, due to some environmental conditions or something wrong inside me. So I perform very slowly. Yeah. So that's exactly I mentioned at the very beginning. Just purely remove some slow savers doesn't solve this problem, because the delay and the latency is a very dynamic behavior of such a system. So today, a group of savers perform very poorly. Next day is another group of savers. Okay, so we show those diagrams as different days. So generate different long tails, as you can see. There is happened all the time. So if you try to catch the so-called criminals, so who cause the long tails, almost everybody become the criminal. It's just happened at different times. Long tail changes over time without obvious pattern. Okay, and also it's not really relate the long tail to different saver types. There's different saver types that all generate long tails to certain extent. Yeah, and if we look into Google machines, Google machines, that is very much like, so we consider roughly 6,000 different machines. You can say the things we talk about wasted time. So Google actually has a very simple solution to long tail problem. When the long tail does happen, they just kill the task and then restart the task. Okay, so we put a name that is called wasted time. You can say the long tail happened all the time. So we started to think about it because everybody could have the low day. Yeah. So every savers could have the chance to produce the long tail. Do they have any patterns? Okay. So our strategy started right now is our luxury is to have such sets of data, real data from data centers. So what about we apply such a data, to understand better, then build up the model so that we can use such a data to train this kind of a model. When the model becomes mature, we can make a good use of such a model to predict the future behavior of the data center. So basically, if I know today I'm working okay, so I got enough workloads to carry out. But if my model can predict it tomorrow, I will be going down in terms of performance, then the system shouldn't assign too much work for me to do tomorrow. So that's the basic ideas. Could we achieve that? So I'll show you some nice results. For example, we started to train our model. So on different months, we apply different AI algorithms. We are trying to achieve the best accuracy of prediction. So here is, you don't have to look into details. So basically the idea is we use 1 month, 2 months data to predict third month, then gradually use entire year data, try to predict next coming month's performance. Yeah. So gradually we could achieve more or less over 90% of accuracy. Yeah, there are only one thing says there, if you notice that there, I just summarize that. Our model works fairly well, But there's one thing we have to be careful. It's about if there's some period of time, for example, the entire data centers stopped for maintenance purpose, yeah, you have to ignore that period of time. Otherwise, you won't be able to train your model properly. So you really need to bear in mind. So the only the high accuracy can be achieved when there are some jobs, to run over the entire data center. Of course, yeah, we learn from historical and also runtime data. So to mention is apart from making use of historic data, we also need this live feeding data at runtime so that we can, in real time readjust our model so that we can achieve much better prediction. How could we achieve that? When I work with Alibaba is a so good company, apart from their live system, like a system they use for e-commerce applications, it's like a Taobao systems, yeah. At the same time, within the company, they also build up a comparable, sizable data center. They call it testing data center. So there's a one-way connection between live system and the testing data center, so that people like me can feel freely without worrying of destroying entire data. I play every possible games with testing data center because the data feeding is only one-dimensional. It's from live, this system. So when I reschedule resources, we can always test my job scheduling first. Make sure within the testing system everything is all right, it's better before I upload, my solution to live system. So I move quickly. Okay, skip the details. That is real diagrams we are make it for Alibaba, for example. So those dots represent slow servers within their systems. Okay, the different colors show different server types. Okay, so that map will give you some ideas. So what is the scale of the system we are dealing with, and also let's give the ideas. How many criminals who produce a long tail inside the system? So it's huge. So if your solution to your boss is just remove slow servers, probably in the end we have to remove an entire data center. Okay, of course on different times. So what we performed is make a good use of historic data, use runtime data that produce a prediction, that part. Okay. Did we do a good job? Yeah, fortunately we did do a very good job. Okay. So the red part is without our system. Okay, that's the long tail, so without using our system. The green part is we did use our system based on accurate prediction. So let me repeat it again. Our approach is very simple. Yeah. So for each server, we predicted the coming performance of each server. If this server performance is going up, we assign probably more workloads to the server. If the server performance is at a level without a big change, we probably maintain a stable of assignment of workloads. If we predict the server's performance is about to go down, we'll reduce the amount of workloads for that server. So in that case, our approach is totally dynamic, adaptive to the current situation of the data center. So of course, we end up with much better results. So the tail become much shorter. Okay. How short we achieved? I'm really proud of to show your slides. So there is a benchmark and contest organized by Microsoft and HP, a consortium of industry partners. So the challenge here, each year everybody can submit your submission to join such a computation. The task is very, very simple. They basically assign you 100 TB sizable data, which is random data. So that you cannot make use of specific structure of such data. So data is random data generated by software. Then by means of your own data center, so everybody can use your own data centers under some standard constraints. Then you measure how quickly you can thought, you can put such a random data in order. So for last 3 years, so Alibaba's system, jointly with these universities, we are lucky to start at top 1 worldwide for last 3 years. The best results, how quick we are, we can actually sort 100 TB random data within less than 400 seconds, which is massive results. It's so quick. Why was so quick? We didn't have a long tail. So another real example, so we apply very similar approach is to taxi and public car service scheduling. Yeah. So we use historical data and runtime data from each taxi. So we use data from OBD, the onboard devices, and also some GPS data. Use such data to train a model so that we can use the model to predict potential customer demands. Yeah. So that is a real system. It's running in the capital of Beijing in China. Okay, that is a big public company called DiDi, D-I-D-I. So that's Chinese DiDi. That is our predictions. The yellow one is ground truth. Okay, the blue one is our prediction. So we can perform it's a fairly accurate prediction for the company. So help the company make their system, their taxi or public car scheduling much more efficient. Okay, save tons of money as well. So very quickly, it will be much shorter than the first problem, but I try to give you an idea. Apart from a long tail problem, but when you bring so many servers all together, when you reach a certain scale, the system become wobbly. So the system becomes very unstable. That's just why. Yeah, because the chances you have so many servers, you can always have some troublemakers. Yeah, it's very much like a human being. If we have a small group of good friends, very good workers, they probably can perform very efficiently. Yeah. But when you have a large quantity of people, then you have a variation. Yeah, you have a variation. So the truth inside the data center, so that is basically the data for Google. As you can see, even in a lucky day, that is red part is failures. You talk about around 10% of failure rate for a system, which is very unusual for standard long high performance computer. They can be much more reliable. But when you talk about the data centers, failure rate can be very high, sky high. Yeah, so what did we do try to resolve such a problem? Okay, first of all, for such a system, we have to find out and also identify the real types or relevant types of failures. Okay, there's one phenomenon within a data center. You actually notice that within such a large-scale system, if there is one failure happens, the failure can, move across the entire system very quickly. Yeah, it's like propagation. They are negatively impacted very quickly. Yeah, so you have to, if you want to sort out the failure situation, you have to move very quickly. So here we talk about very rapid, very fast recovery. If you don't do that very quickly, your system will start to melt down. That is the words used by Google. Yeah, system can melt down very quickly. So do something very quick. So what we did is we had very intensive interactions with a company like Google, like Alibaba. Particularly when we talk to Google, when we challenged them, so how do, of course they will cover their own tail. They didn't tell us how they basically how they perform error recovery. Yeah, the standard way to do that is kill the problem process and restart it again. But that is, cannot be very efficient. When we look through the data from Google, we find out there are so many of we call it data loops there. Data loop means you kill the task, restart it, then you have to kill it again. So you waste so many resources without making useful progress. Because that's the issue. You don't want really to do that. So in theory, in principle, the much better idea is to make a good use of checkpointing, right? So you save important states of each application. If something wrong, you can roll back to previous state, then not restart it again. You just have to roll back to last, the right, correct state of the application. But for large-scale data centers, the challenge here is we cannot afford to save too large amount of data, status information. Because if each application state become very big, there is no way for us to recover very quickly. Yeah. So jointly with Google and Alibaba, we developed a new approach, is so-called soft state-based recovery. So for each applications, we managed to identify the minimum amount of status information we have to save in case we need to perform recovery. Okay, so each time the overhead is fairly low. When we have to recovery, we start to collect information from labor savers, so that for the purpose of recovery, we can very quickly form the hard state for the purpose of recovery. So that's the idea. Start. Oh, sorry. So we manage, if you notice, you cannot really tell the difference, the dark one and the green one. But that gives you ideas. By means of our approaches, the overheads generated for the purpose of recovery is quite limited, okay, because the use of soft states, okay, soft states, so that we basically achieve fault tolerance, so much better, much quicker recovery, but without to have massive overheads there. Okay. So that's another technologies. We make the system much more stable. Hence, when we are doing such kind of computations, so our system is much more reliable actually. So because we can perform much quicker recovery. Yeah, slightly reaching the end of my talk today. I try to summarize from our research experience. We found, you probably already realized, so our research is largely based industrial, the real data. Okay, so that is my own opinion. Doesn't matter, which important area of cloud computing or data center you are involved. You have to get your hands dirty. You have to have experience with real data centers. Otherwise, you only talk about the challenging issues at the most at conceptual level. You don't have a first-hand hands. Scale, is another keyword here. Scale of cloud computing systems introduce non-traditional challenges. So hopefully you understand the challenges, the problems, the difficulties. We have been discussions today so far are quite unique, quite specific to massive scale computing systems. Last but not least, I think the way we make a good use of machine learning, good use of AI, actually shows some good sign to direction of researches. So including event forecasting, making the cloud ready for robotics, so provide a better backend support for robotics applications. So out of many years research in this domain, we obviously have academic outputs. So there's a long list of papers published in IEEE transactions. So you can Google it, by means of my name is very easy. So another output from our research is because our research is touch ground, engage with industry. So I ask myself, why not make, why not to make some money out of it? So we start a company. The company is doing very well now. So we are inside a major commercial building in Leeds. So we have this company doing data analysis for the purpose of improving efficiency of any large-scale system, including data centers. Okay, thank you. I hope our research shows some new dawn to power clouds for robotics. Thank you. I'm happy to answer any question. Yes?
Is part of your data publicly available? Because I can imagine this is quite sensitive.
Yes and no. Okay. So some companies started to publish data to public domain. For example, the data when we used with Google, it was confidential. But now, if you search in the internet, that's 1 month's data from Google. Now actually is publicly available now. Of course, the data you got, which has been normalized, if you like, they remove any sensitive details. So which means that the data you got probably not as details as we have in hand. But you do find some publicly available data. From Google, for example. I remember Google have at least so far released at least 3 different sets of operational data. Okay, you can search the internet. One small amount of data, for example, you or your student can start with small sets of data, which is just week, 6 days of data. Then there's large data is for months. The recent release of data is for 2 months. Okay, so you can play with the size of data. I also understand that Alibaba at least plans to do the same. Okay, I understand towards the end of this year, Alibaba will put 1 instance of their operational data on the internet, so you can search for it.
if I understood well, when you want to predict, for instance, the behavior of one server, will it be well tomorrow if it behaves well today or bad today?
Yeah.
You essentially do some kind of time series analysis or something like that.
Yes.
Do they provide you enough information to be able to dig a little more on the reason why this is happening? Because it's difficult to understand that a server that is a piece of hardware would not work properly 2 days later. So the reason must be something that I would like to know, for instance, if it's a poor usage of resources, poor allocation of resources for some reason, for example, it was allocating a CPU-intensive task to some server that did not have a very good CPU, or they allocated a very memory-intensive task to a server that had limited memory or something like that. Is it something like that? Poor allocation or bad allocation of resources?
It's a very good question. So to answer your question precisely, started with Google investigation. They actually identify around 22 different reasons.
Okay.
Yeah. So there are so many reasons, including the garbage collection, for example. Yeah. So it's like a person could become ill, but due to so many different reasons. Yeah, you said that. So our solution is not to try to cure the problem. We just find the problem. Even you don't feel well today, the system in whole still can fulfill the task, you can say. So if I can predict, you will be complete tomorrow, I will reduce your workload. But I do not try to find the reason why you will become complete tomorrow. Okay? But our research actually started from beginning, try to analyze different reasons. So we decided to go for this solution. It's very much like we can produce a better results to you, but we cannot really cure the different reasons.
I understand.
Yeah.
The idea would be to go further and try to see if, because of course, what you will try to do is to have a better control over what you're doing. Yeah. And so if you want to have a better control, you have to be able to identify.
Understand.
So I think that as in many areas, we see that if you do nothing, you have poor result, and sometimes doing something that is very common sense gives you a lot of amelioration and enhancements. And then if you want to go further, then you have to dig a little more. And that would be the idea, because I think that your ideas are very good.
Understand, yeah. Thank you. I still have a space to improve. If I can perform good enough prediction with some specific reason, then I can generate even much better scheduling approach.
But of course, it's like, those like Pareto laws that says that the 80% enhancement, you get it by having a 20% effort. Yeah. But if you want to get the other 20%, you have to put 80% of effort to go. And so I can imagine that this will be the case, in fact. Yeah. We can have a 2/3 enhancement, but if you want to go further, it will cost you a lot more. You have to invest a lot more.
Exactly. We perfectly understand the issue there. For example, the entire project, if the long tail is due to large amount of intermediate data, our project doesn't work. Yeah. So server still okay, but you still have to deal with a large amount of data, still generate a long tail. So if we have some kind of detection mechanism to say this particular long tail will be generated by unbalanced data, then you can start a different solution to do it.
Indeed. It's very good for software engineer to know that if you don't care about how you distribute the data to the different tasks, it's very poor. And indeed, I would imagine, for instance, we talk a lot about the map-reduce things these days. And when we see your data, I could imagine that in the map phase, you go very fast. And then it's the reduce phase that produces the long tail. So you have to think a lot more about how to organize this reduce part of the...
Fantastic. We did have one paper try to deal with such a phenomenon. You know, map stage is so quick, but the reduce stage become very, very slow. So we are trying to insert one piece of but very simple software so that you know, during the intermediate stage, we can somehow rebalance the data between servers. So in that way, you can cut off the tail you know, dramatically, cut it short.
Of course, a lot of the reduce are doing, in fact, a kind of list processing to aggregate the data. And yet, when you turn out to a tree, you can be much better in your algorithm.
Yes, please.
I wanted to ask if your research starts when the data reaches the data center. Because in robotics, if you have a real-time algorithm to be executed, there are two delays. The first, the delay when you send the data, the network delay, essentially. And the second is the computational delay. So what about the network delay? Can we do something? Have you investigated something like that, either in a local network or?
Yeah, we do have yes, here is we more or less talk about computational delay in your term, right? So the real-time like data transmission delays, we do have some work. Hopefully you can find out more you know, solutions in that domain tomorrow. I think Professor Dimbo will give his keynote speech. So I do know his solution. So we basically started research to try to build up an entire operating system, which have to guarantee you know, 3 different kind of real-time requirements, like on-site and the data transmission and the data center side. So only bring those 3 things together, you can in total guarantee. Yeah, we understand that. But my talk today is try to give you an idea on the data center side. I assuming you have you know, limited opportunity to listen to this part of research. So hopefully I can give you some ideas of what we're doing on back-end data center. Okay, is that all? Okay, thank you.